Hello all, my name is Santosh and today we'll be seeing about Boolean Algebra. Let's go on with it. So these are the topics that we'll be covering today. Boolean Algebra, laws of Boolean Algebra and theorems and postulates related to it. So what is Boolean Algebra? Boolean Algebra is a special branch of algebra which is mostly used in digital electronics. This was invented in the year 1854 by an English mathematician George Boole. And Boolean algebra is a method of simplifying logical circuits. So this Boolean algebra is used to simplify the circuits, like if you're using many number of gates or the logical gates known as the AND gate, NOR gate, NAND gate, and the NOT gate. Using this Boolean algebra, you can simplify them by making the program simple, like just having a NAND gate or an OR gate alone, instead of having many number of gates in it. And this is also called as a switching algebra. We can represent the functioning of logical circuits by using numbers, by following some rules, which are as well known as laws of Boolean algebra. We can also make the calculations and logical operations of the circuit even faster by following some theorems. Those theorems are known as the theorems of Boolean algebra. This is the scientist George Boole. So these are the properties. The first property is the closure property. A set S is closed with respect to a binary operator if. For every pair of elements, the binary operator specifies a rule for obtaining a unique element of S. Example, the set of natural numbers n equals to 1, 2, 3, 4 up to infinity is closed with respect to the binary operator plus by the rule of arithmetic addition. Since for any A or B belonging to n, we obtain a unique C belongs to n by operation A plus B equals to C. The set of natural numbers is not closed with respect to the binary operation minus by the rules of arithmetic subtraction, because 2 minus 3 equals to minus 1 and that does not belong to n. So this is what is closure property, where we say that if you have A plus B, an operation taking place as A plus B equals to C, then every time the C will always be a set of n. And if you're having A minus B equals to C, then the C might not be a set of n itself, though A and B are a set of n. Associative property. A binary operator star on a set S is said to be associative whenever x star y star z equals to x star y star z. So here it means like if you're multiplying 3 into 2 and that gives you 6, then 2 into 3 is also 6. That is, even if you interchange the numbers, the value will be the same or the output is the same. That's what is given in the associative property. And now commutative law. A binary operator star on a set S is said to be commutative whenever x star y equals to y star x for all x y belongs to S. So it's just like the associative law, but over here you only have 2 variables and in associative you have 3 variables. That is, for associative it might be A into B into C equals to B into C into A. Even if you change the terms in different ways, they'll be the same. That's how it is for commutative law also. But over here you just deal with 2 variables, that is x and y, or else A and B, etc. So now identity elements. So a set S is said to have an identity element with respect to a binary operator S if there exists an element E that belongs to S with the property E star X equals to X star E. So let's take an example of X into 1, which is equals to 1 into X also. So the element E is present, it is an identity element which does not change the value of X itself. Something like A plus 0 or x plus 0, which is equal to x itself, where it does not change the value of x at all. That's what is identity element. So now let's go for inverse. Now set S has having the identity element E with respect to a binary operator star is said to have an inverse whenever for every x belongs to S, there exists an element y belongs to S such that x star y equals to E. So taking an example like x star x inverse or else x divided by x inverse or x into x inverse, you'll be having the same value as 1, or x plus x inverse that is equals to 0. Like you can see over here, A plus A inverse that is minus A, which is equals to 0. That's what is inverse. So now distributive law. If star and dot are two binary operators on a set S, star is said to be the distributive star is said to be distributive over dot whenever x star y dot z equals to x star y dot x star z. So something like you can use an operation between x and y dot z that can be either addition or multiplication or division, and it will be equal to x plus that operation dot x and that operation between x and z. Depending on the operation, it the answer might vary over here. So those are the laws, and now we are seeing about the theorems. And over here we'll be studying about 6 theorems and 4 postulates. So the first one is postulate number 2, which says that x plus 0, which is equal to 0. So let's take x as 0 or 1 as a binary digit. So it does not change the value of x no matter what it is. It will remain as x itself. And then x dot 1 is also equal to x. It's just like a normal addition or multiplication where x plus 0 or anything plus 0 is equals to x itself, and anything into 1 is also equal to x. That is something like 1 into 1 or 2 into 1, which is equals to 1, and 1 plus 0 is also equal to 1. The next postulate is fifth postulate, where x plus x dash is equal to 1. Like we saw before, where you had something like a plus a dash or a inverse, which is equals to 1, and x dot x dash is equal to 0. And then the theorem 1, where x plus x equals to x, and x into x is also equal to x. So now the theorem 2, x plus 1 equals to 1, and x dot 0 equals to 0, etc. We have all the theorems listed over here that we'll be using in Boolean algebra. So let's see about few problems related to that, where we'll be using all these theorems. So we'll have to prove that the LHS and RHS are equal. So let's take the LHS and open up the brackets now. We'll just multiply all the terms over here. So it will be x dot x plus x dot z plus y dot x plus y dot z. So this can be written as, like we saw the previous theorems, that is x into x equals to x. So it will just remain as x itself. Yes. So here let's take x common. So it will be 1 plus z. Or before that, x plus 1 equals to 1. Just like that over here, it will be 1 plus z equals to 1. So it's going to be x into 1 plus z, that is 1. So x into 1 is 1. So x into 1 is x. Take x common. It will be 1 plus 1 right on this side. Then again it will be x plus yz. And this is what is the required answer. So we proved that x plus y into x plus z equals to x plus yz. So now let's go for the next problem. Over here, you have the problem as x plus y, xy plus xz plus y dash z, yz dash equals to xz plus yz dash. We need to prove that LHS is equal to RHS. So first, let's multiply the terms z plus z dash and all the other terms that are missing in the variables. So now opening up the brackets now. And now here you know that x plus x equal to x. So xyz plus xyz is also equal to xyz only. So write it as xyz as itself. Xyz dash and xyz dash is also written as xyz dash itself as a single term. Now it will be x y dash plus x dash y z dash. So let's just rearrange the terms now. Now we'll take out exit common over here. And over here we'll take out y z dash common. As you know from the theorems and postulates, that is y plus y dash and x plus x dash will be equal to 0. I mean, it will be equal to 1. So it will just be as xz plus yz dash. So that's it. Thank you.